You're watching PowerNation.
From old reliable to wow, we've got big plans for this small block Chevy.
Today on Engine Power, we bring our backyard build into the shop to give it a slew of power upgrades.
Hey everybody, here in Engine Power we have one of our old favorites back, and it's probably pretty recognizable to you. It's a small block Chevy 350 that was pretty unique because it never even came into the shop. We did all the work out back in our parking lot, just like you guys would at home. Now we accidentally picked the hottest day of the year to do that, but after a long day of thrashing, we even started it up right out on the pavement.
After all of that fun, we brought it back into the shop, hooked it to the dyno to see how it runs. Now, quite frankly, it did rather well. We have a very distinctive looking setup, so you would probably remember both the dyno session and the build. But just in case you don't, have a look at this. Frankie told me he got a good deal on a throttle body injection small block along with some parts that had been ordered for the seller's engine build. Tearing into an engine is kind of like opening a Christmas present. Sometimes it's great, sometimes it's terrible, and sometimes, like this small block, it's pretty good. We did hit a couple of snags along the way, such as underneath the valve cover.
Whoa, look at that. A couple of the oil shrouders are broken. I actually saw that, one of those on the other head, but there's a couple in this head that are broken.
I have never seen that before.
Oh, I mean, just some water and some oil.
There's
and some oil water. I don't see any chunks though.
Man, a little bit of.
That's not too bad.
That's not total milkshake. It's kind of dirty.
Yeah. Nasty.
Oh, this is a horrible job. That's what cardboard's for.
Yep. After cleaning the cylinder heads by hand, we installed new seals and valve springs designed for a hydraulic roller cam. Then we freshened up the cylinder bores using a 320 grit ball hone. This establishes a new finish for the fresh piston rings to seat on. We used engine oil as a lubricant and turned the hone at about 300 RPM to achieve roughly a 45-degree included angle on the crosshatch.
To measure main bearing clearance, we used Plastigauge. After torquing the caps down and removing them, we checked the compressed plastic against the gauge. We had about 2 thousandths clearance. The crankshaft is a 10 thousandths under and is part of a kit that includes bearings. The mains are torqued to 65 pound-feet.
A new cam was included in our engine purchase. It's a hydraulic roller from Comp with a fairly sporty grind. A new double roller timing set came next. We reused the pistons, but since the rings are a wear item, they were replaced with a set of OEM style pieces.
There's no way we'll build an engine without degreeing the cam. It came in at 106 degrees of intake center line, which is 4 degrees advanced. A fresh oil pump and pickup assembly went in. Retrofit hydraulic lifters were part of the cam kit. I wish that crew would come and do our work that normally does it.
The ninjas?
All the ninjas.
The Midnight Ninjas? Yeah. The heads were torqued in 3 equal steps to 65 pound-feet. The push rods were part of the cam kit and are shorter than the originals.
We had a dual plane Wyand Speed Warrior intake in our shop. It's a great choice for this engine. A Street Demon carb was next, followed by our Derby headers. All right, here we go.
There you go.
Solid.
You like those? Borrowed those from the guys down in Carcass.
I knew we'd get use out of them one day.
Then we ran fuel and electrical lines and fired this small block up.
When we got the engine back into the shop, it went straight into the dyno cell. Smooth!
Yeah.
Good oil pressure. No way.
Yeah, look at that.
No way. Woo! I
Yeah.
cannot wait to see what the timing is right there, because that actually made decent power.
That's not bad.
The Chevy put out 276 horsepower at 4,800 RPM and 345 pound-feet of torque at 3,200 RPM. Coming up, static compression is important, but dynamic compression tells the full story. We're back on the Small Block Chevy 350 backyard build. We have a bunch of parts in-house to upgrade this power plant, and it will get a big power increase over the modest driveway build you've seen here before. Last time we did this, it was like 600 degrees out.
No, by that time it was all dark, remember? It was only, like 90 degrees.
The teardown begins by removing these notoriously obnoxious derby headers.
Takes a little bit of work, huh?
I'm still working on it. I was very happy with how it ran.
Yeah.
And since this engine is getting better induction and an upgraded rotating assembly, it has to come completely apart. Even though this small block didn't make crazy power, the spark plugs indicate that the engine had a great tune-up in it. This side's the same way. Not bad for a parking lot hone job. She's sealed up nice.
Yeah. I mean, it didn't make a ton of power, but when it was dynoed, it ran really good. It didn't smoke, it didn't miss. I mean, can't complain for being built in the parking lot.
Stuck down.
You can get it? Oh, yeah, there you go.
Powered off there. There we go.
Still looks good.
A brand new engine,
Yeah.
sort of, kind of, not really. Whoa, come back here.
Since we won't be reusing the cylinder heads or valve train, we'll skip removing the rockers and push rods and jump straight to unbolting the heads.
Nice.
Wow, the chambers look good, not wet. Looks like it was running really nice.
Actually, yes, chambers are all dry. Cylinders are dry. Now, I wasn't expecting a race engine, but the cylinders look decent.
Yeah.
If you don't see anything that's migrating oil-wise up into the chamber and things like that,
Yeah.
it was running fine.
I mean, for the way it looked before, it looks just as good now, like
Yeah.
it wasn't perfect when we started, so it's not perfect now, but it still looks good and there wasn't any major problems. It looks like it ran really nice, and we know that it did because we dynoed it, so yeah.
Beauty. We're not going to use these lifters again, I don't think, are we?
No, but I think we'll keep them just
Yeah.
in case. There's probably nothing wrong with them, so
Yeah.
we can keep them for another project and hydraulic roller, so don't need to keep them in order or anything. So.
Right. Brand new, everything looks fantastical, though. I'll take it.
The great part about a one-piece oil pan gasket? If you don't go too heavy on the silicone when installing it, you can generally reuse them later. This one looks really clean and was only installed last year, so we'll reuse it.
This OE replacement balancer worked great for the first build, but since we're upping the power, we'll replace it with an SFI approved piece.
Before the bolts can come out, the locking plate tabs must be bent back out of the way.
Because the engine has a hydraulic roller cam, a camshaft thrust button was used to keep the cam located. We'll save it to use on the new camshaft. Look at that. Brandy new.
I mean, they basically are. Always protect the crankshaft by covering the rod bolts before removing the connecting rods.
Oh yeah.
Pretty good, yeah. Those look pretty good for used pistons. And I mean really used pistons.
Hey,
What?
we got to keep going here. I know you're
Just reminiscing, man.
You're living in the past.
Yeah.
Live in the now. Ooh. It's a shame to tear this one down, but we are doing it for a good reason.
Yeah, more power is always a good reason, but it looks really, really nice, so that's a good sign. Small block Chevy builds are a dime a dozen, and we have done our fair share. So with this one, we're going to do something that is a little bit different. We haven't covered that much, and you might not have seen, but it's universal to all engines, and that is cover dynamic compression ratio. Normally, the rule back in the day was that 11:1 static compression ratio was the limit for pump gas, but there's a few more factors that go into the actual octane rating your fuel needs, and the bigger one is dynamic compression ratio. Static compression ratio uses the distance between the piston at bottom dead center and top dead center during its calculation, but dynamic compression ratio factors in when the intake valve closes, because no air can actually be compressed inside the cylinder until both valves are closed. Because it's based off when the intake valve closes, cam size and intake centerline placement are huge factors. For our engine, we're going to run a static compression ratio that you would normally think is not possible on pump gas, but because of our dynamic compression ratio, it's going to run just fine.
Spoken like a true engine builder.
I try sometimes. Up next, we prep the small block to receive forged pistons and upgraded cylinder heads.
The purpose of this build is to show you that the octane rating of your fuel is not determined solely by static compression ratio. We are retaining the stock block and stock crankshaft because they will be sufficient for our power level, but we are upgrading the rest of the internal components with things we've picked up from Summit Racing equipment, and that's going to help us make that happen. And it all starts with the connecting rods. They are from Scat, and they are a 40-340 material with an I-beam design. They are 5/700 center-to-center length like a stock small block Chevy with a 927 wrist pin, but this one contains a bushing so we can run floating wrist pins. We're getting rid of the press fit. They are also retained by 8740 ARP rod bolts. Those rods will be swinging around some Icon forged pistons. These are a 2618 alloy and have a 16th, 16th, 3/16 ring pack. They also have a 927 wrist pin, but these pistons have something that you normally don't see us have, and that is a 13cc effective dome. That will help us get our static compression ratio up to where we want it for this build. Filling up those ring grooves are a set of total seal rings. Now, these are a special set of rings that have a top ring that is gas ported. We want that benefit of gas porting, but we didn't have any gas ports in the pistons themselves, so we will really benefit from their extra sealing ability. Also, we are going to do some special stuff with the camshafts. You see two camshafts sitting here, which is odd, but one is a large one and one is a not so large one, and they are both a TrackMax from TrickFlow. The camshaft is what affects dynamic compression, so depending on where the cam is and how big it is, that determines our dynamic compression. The smaller of the two has a duration at 50 thousandths lift of 230 degrees on the intake, 234 degrees on the exhaust, and they are on a 110 degree lobe separation. The larger one is a 246 at 50 on the intake, 254 on the exhaust on a 112 degree. Both camshafts will work for our application, but that is strictly dependent on where the intake center line falls on the camshaft. So we have a billet timing set with a 9-position keyway on the crank side to help adjust it where we want it. On the induction side, we're keeping it simple and we're keeping it classy. These are TrickFlow's Super 23° series fast as cast 195cc intake port heads. These do not have any CNCing done. The port is cast to the right shape, so they flow great. They have a 2020 intake, 1600 exhaust. They're both swirl polished stainless, and they're housed in a 62cc chamber. They also have a 460 diameter spring set up for our hydraulic rollers. And for the top of the induction, we're going to keep the RPM range in a manageable spot, so we have a TrickFlow street burner dual plane intake manifold. Like always, we're holding everything together with ARP fasteners. Before we can install any of these parts, we have some work to do, namely get the crankshaft rebalanced and do a bunch of prep work on the block, like make our pistons fit. So, off to the races.
A solid carbide tip scraper might set you back $30 or more, but it makes quick work of removing old gasket material without damaging the surface. We'll punch out the cam bearings before deburring and cleaning the engine. This prevents metal shavings from getting behind the bearings during machining. We'll also remove the oil gallery threaded and pressed in plugs so the galleries can be cleaned before assembly.
Using a metal file, we'll gently deburr the block and main caps. It doesn't take much. We're only removing a tiny amount of metal to round off sharp edges, which could cut you. It also helps remove stress risers where cracks could start. This takes a bit of time, but it's very satisfying when you're done. We'll run the engine in the jet washer to remove the metal shavings. We don't want them getting into the cylinder hone. Up next, setting the correct piston skirt clearance helps make sure your engine runs right and runs long.
We are all about horsepower here, and that means increasing cylinder pressure. And we've been talking about how that correlates to the fuel octane you need, but it also determines what kind of spark plug you need to run. Now, there's a bunch of different styles and manufacturers of spark plug, but in today's Summit Tech Tip, we're going to be talking about spark plug heat range. Now, the heat range determines how much heat is transferred from the spark plug itself through the threads into the cylinder head and onto the cooling system. A hotter spark plug has less contact between the porcelain and the threads of the plug, so it will transfer less heat, while a colder plug has more contact between the porcelain and the threads and will transfer more heat. Here's an example of a cold spark plug and a hot spark plug, and you can see the difference in how much contact the porcelain has with the threads. A spark plug that is too cold will not retain enough heat to burn off carbon deposits and can eventually foul, while a spark plug that is too hot can become a potential point for pre-ignition, which is when the fuel-air mixture is lit long before we want it to and is completely different from detonation but very harmful to the internal components of the engine. Every manufacturer has a different heat range that correlates to how much heat the spark plug will transfer, but if you know the style and size of the spark plug you're going to be using, it's pretty easy to cross-reference heat ranges between brands. Just like everything else in engine building, this is application specific to how much power you're going to make, so you definitely need to know the heat ranges of the manufacturer you're going to be working with. Something to think about when you're trying to make more power. If you need help finding the right plug for your application, reach out to the experts at Summit Racing Equipment.
There isn't anything that bolts on the inside or outside of an engine that can't benefit from a high-quality fastener, and that's why you see a lot of ARP around here. We wanted to upgrade the fasteners in our engine, and that includes the main, so we ordered up one of their main bolt kits. This one has 8740 chrome moly fasteners that have 180,000 psi of tensile strength. That far exceeds the tensile strength of an OEM bolt and even a grade 8. The kits come with everything you need, including lube and detailed instructions. The instructions are very important because since these are not an OEM fastener, they take a higher torque value. You can't just look at an OEM book and get the torque. You have to follow the instructions to get it right. We are going to get the mains torqued on and then get it in the hone. We apply ultra torque lube under the bolt heads and on the threads themselves. You'll notice there's no lube under the washer. This is a critical step that ensures torque accuracy. Lubrication under the washer can overstress the fastener even at the correct torque value because the washer acts like a bearing if lubed on both sides. The bolts are torqued to 70 pound-feet. With our block fixtured up in our Sun SV15, it's time to set one of the most critical clearances in an engine, piston skirt clearance. Now, that is dependent on a couple of different things, and this is like everything else, it's application specific. It depends on what the piston is made out of and what you are going to be doing with the engine, because the exact same piston design has to do a whole bunch of different things related to heat, so it can be used in a variety of applications. This handy dandy sheet is included with the pistons to give you a guideline of where to set your clearance depending on what you're doing. From street naturally aspirated all the way through to marine supercharged, and the clearances will vary quite a bit because this is a 2618 alloy and it has a high rate of expansion, and that will vary in clearance from a minimum of 3.5 thousandths all the way up to 9 thousandths on some applications. That sounds like a lot of clearance because it is. Engines that generate a lot of cylinder pressure generate a lot of heat, and when that heat is made, the piston swells faster than the block can keep up with it. So if you don't have that additional clearance, you run the risk of damaging both the cylinder and the piston itself. For our application, which is essentially an R&D engine, we are going to set the piston clearance at 6 thousandths, and that clearance is determined by the manufacturer as well. The piston manufacturer determines where they want the skirt measured for proper clearance, and these have a mark where you put the anvils of your micrometer to get the accurate measurement. Our skirts are measuring 4056 and 2/10. That means with our additional clearance, our final bore size will be 4062 and 2/10 thousandths. It's a little bit bigger than the final 4060 because the block is 40 over now. I have a lot of honing I have to do. I have to rough the cylinders out, put the torque plate on, and run them all to final size. So the next time you see this, it'll be ready to assemble. For more information on anything you've seen today, please visit our website.
Somebody call a psychiatrist because we've developed an unhealthy compression obsession.
There's a limit on how much compression you can safely build using pump gas, and today we just might find it. Today on Engine Power, we are getting back on the revamping of our backyard small block Chevy build into a Dyno Mule so we can do a little bit of R&D. We're going to show you today how you can run your static compression higher than you normally think you ever could and still run it on pump gas. We've had to ditch most of the stock parts in favor of some shiny new high performance ones to get the job done. If you want to see what we've done to this engine to get it to this point, watch this. Frankie hunted down a worn-out small block that also came with some parts intended for the seller's engine project. After a complete rebuild, including new springs, a bigger cam, and a bunch of top-end components, we fired it up just for fun in the parking lot. Then we rolled it into the dyno cell.
No way.
Yeah, look at that.
No way.
Woo! The Chevy was good for 276 horsepower and 345 pound-feet of torque. But we want more power, and for this build, part of that equation is increasing dynamic compression.
After teardown and inspection, we prepped the engine for forged rods and pistons, gas-ported rings, a couple of camshaft choices, adjustable timing set, 195cc heads, dual-plane intake, and a user-friendly EFI system. To achieve the proper cylinder wall finish, and to let us install bigger, better pistons, the cylinders were honed to 4062 and 2/10.
You know what you're gonna say?
I think so.
All right, go ahead.
I don't know.
Oh,
there you go. We also went ahead and tapped our oil galleries in the front for some threaded plugs, deburred most of the block, and cleaned up some of our oil galleries to improve oil flow. Now, static compression ratio, you're probably wondering how we're going to run something that's so high and still be on pump gas. And that's because static compression ratio is only part of the equation. Another huge part of it is dynamic compression ratio. We talked about what that was before, and today we're going to talk about how you can actually affect it with the components you choose for your engine. Now, since this is an R&D engine, not only are we going to cover the tech, but we're also going to show you how it improves performance or not on the dyno. This thing looks ready, so let's move on to assembly.
time to get working.
All right. As always, the first part of the assembly process is measuring oil clearance on our main bearings. Since the undersized bearings are basically brand new, we are going to reuse them. The ARP main bolt kit is torqued to 70 pound-feet, just like final assembly. For each journal, we'll set our micrometer to the journal size and use the micrometer to zero out the dial bore gauge. Our clearances come in between 19 and 20 10,000ths. That sounds a little tight, but it's well within the OE spec. We'll repeat the process for all the rods, which are within stock Chevy specification as well. Next, the camshaft bearings are finally pressed in.
The pistons will receive Total Seal's gas-ported top ring set. This gives you all of the benefits of a horizontal gas-ported piston without having to machine the piston itself. Since our Dyno Mule engine will probably see some abuse, we'll gap the ring a little larger to 22 thousandths on the top ring and 24 thousandths on the second ring. We'll go slowly and check our work often. Not to be overlooked is deburring the ring with a fine India stone after it's been filed. This ensures the ring doesn't damage the piston or the cylinder wall.
With everything clean, we'll lube up the bearings and reinstall our rebalanced and polished stock crankshaft. This was done by our favorite machine shop, Shacklet Automotive Machine. Just like before, the final torque value on the 4-bolt mains is 70 pound-feet.
It's time to put a cam in our engine, which brings us to why we are doing this entire operation, adjusting dynamic compression ratio. A lot of the times people get hung up on just static compression ratio to determine the octane and fuel they will use, when dynamic compression ratio is just as important as static. It is calculated the same way, but you have to know a couple different things about your engine. One is the connecting rod length, and two, where the intake valve closes in the cycle, and that is directly affected by the camshaft. To calculate dynamic, we have to use something called effective stroke, and that is the amount of stroke left after the intake valve closes. Now, that is a large equation, and if you're good at trigonometry, you can get it figured out. But if you know all of your numbers, you can plug it into a few online resources, and the math will be done for you.
When we built our engine in the parking lot, it had a measured static compression ratio of 8.82 to 1 and had a dynamic of 7.27 to 1. Now, with our new parts like our 13cc effective dome, our head gasket size, and our head chamber size, we have a measured static compression ratio of 13.15 to 1. Now, that seems high, but we're going to use camshaft selection to make our dynamic compression ratio pretty manageable. We have two TrickFlow TrackMax hydraulic roller camshafts on the table. One that's a little bit smaller, one that's a little bit bigger. The smaller one has durations at 50 thousandths lift of 230 degrees on the intake and 234 degrees on the exhaust on a 110 degree lobe separation angle. The larger camshaft has durations at 50 thousandths lift of 246 degrees on the intake and 254 degrees on the exhaust on a 112 degree lobe separation angle. Because of our part selection and where we want this engine to make power, we're going to use the smaller of the two camshafts. We also have a Summit Racing Billet double row timing set that is adjustable, so we can dial in our intake valve center line to where we need it to be manageable and also run pump gas on the dyno.
Coming up, we get this small block together and get it on the dyno. Before the camshaft can go in, our threaded oil gallery plugs must be installed.
You're probably wondering why we chose the smaller of the two camshafts. And because of our parts choice and the purpose of this exercise, we want our engine to make power a little bit lower in the RPM range. It's also going to affect our dynamic compression ratio. Generally, as a rule, choosing a shorter duration camshaft will increase dynamic compression, and choosing a longer duration camshaft will decrease it. We're also going to be able to adjust that, like we said, with the intake valve center line. Advancing the camshaft will make the intake valve close sooner, increasing effective stroke. And retarding the camshaft will make it close later, decreasing effective stroke.
With the timing set snug down, we'll temporarily install the number 1 piston without rings so we can degree the camshaft. We're putting the cam's intake center line in very late at 112.75 degrees, which is 2.75 degrees retarded.
Because we are using a stock crankshaft, we know our physical stroke is 3-inch 480 thousandths, but because of where our intake centerline is placed, our effective stroke is reduced down to 2-inch 341 thousandths, and that makes our dynamic compression ratio 9.17 to 1. But what does that number actually mean? To us, it's very important because we know the dynamic compression of all the engines we've built. We've ran things on pump gas all the way down at 6.2 to 1, all the way up to 9.24 to 1. So this, although it's on the top end of the range, will run just fine with that cylinder pressure on pump gas.
In order to accurately check piston to valve clearance, we're installing a set of Cometic MLS head gaskets with a 4060 bore and a 40 thousandths compressed thickness. With cylinder 1's valve train mocked up, we'll start by checking the exhaust valve clearance at 10 degrees before TDC on split overlap. It comes in at 225 thousandths. Doing the same for the intake at 10 degrees after TDC on split overlap, it comes in at 249 thousandths. That's plenty of clearance.
With all of the Icon pistons hung on the full floating Scat rods, the Total Seal ring pack can go on. The pistons get a light coat of Total Seal assembly lube, which is worked into the ring lands to ensure proper break-in. The cylinder walls are lubed as well. An ARP tapered ring compressor at 4060 bore makes installing the piston assemblies much easier. After breaking the rod bolts loose, they get torqued to 43 pound-feet to make sure they do not exceed the manufacturer's maximum stretch of 47 10/1000ths.
We are reusing the stock timing cover, but the smaller 6 5/8 inch SFI approved balancer doesn't line up with our stock 7-inch timing pointer. So we got a Moroso adjustable one to replace it. All we got to do is switch them out.
Whoa!
An ARP oil pump stud will retain the Melling oil pump. It's torqued to 55 pound-feet. A little fresh silicone in the corners and the one-piece oil pan gasket and stock oil pan are reinstalled. They're held down with ARP 12-point stainless fasteners.
Up next, the Chevy receives free-flowing cylinder heads and a no-nonsense EFI system. We've only got the top end to complete before this small block heads to the dyno cell. After a coating of break-in oil, the comp hydraulic roller lifters we got from Summit Racing slide in. The heads are Trick Flow Super 23 degree Fast as Cast 195 cc's. As with all small block Chevys, the head bolts receive ultra torque under the heads and sealant on the threads.
Hey, that rhymes.
The heads are torqued in 3 equal steps to 70 pound-feet. The 7/400 long comp push rods are lubed and dropped in. Trick Flow's 1.5 ratio full roller rockers are dropped on and preload is set to 1/2 turn past 0 lash.
We'll lay some silicone around the water ports before installing the intake manifold gaskets. After getting an immaculate bead of silicone on the china walls, the Trick Flow dual plane street burner intake manifold, with added coolant crossovers, is gently laid into position. ARP's 12-point stainless intake manifold bolt kit holds it down. The heads are sealed up with some Trick Flow tall cast aluminum valve covers.
Picking the right flywheel for your street or strip vehicle is much more important than you think, and today's tech tip is all about the different kinds of flywheels, and we have a few different options on the table from Summit Racing to help us out. The first kind is gray cast iron, and this is generally used by OE manufacturers because it's cost effective and easy to produce and will generally hold up to the power levels and RPM range of a stock vehicle. If they are going to build a vehicle that's going to see more abuse, like a truck or a high-performance car, they can use a nodular cast iron flywheel. The big difference between the two is that in nodular cast iron, the graphite and carbon molecules are in the form of spheres instead of flakes. And this doesn't exactly increase the tensile strength of the material, but it does improve its load impact resistance for higher abuse situations. If you're going full-on high performance, the next step is a billet steel flywheel. Like the name suggests, it's machined from one giant chunk of steel, and it's going to be much stronger than the cast versions. If you're building any kind of high performance vehicle, this is a go-to. If you're going to be doing some form of racing that requires the engine to accelerate and decelerate quickly, a great way to help that is to reduce rotating weight, and you can do that with an aluminum flywheel. This is machined from a big chunk of aluminum, so it's still SFI approved, but it has an insert here that's either bolted or riveted in for the clutch material to contact. These are great in racing, but if you're building a high-performance street car, the extra inertia and heat cycle durability of a billet steel flywheel is probably going to be the better choice. If you need help figuring out what type of flywheel is best for your application, you can talk to the experts at Summit Racing Equipment. We're using a billet steel externally balanced flywheel on our engine. It's torqued to 80 pound-feet.
We are getting dangerously close to firing up our small block on the dyno, but to do that we need to top off the induction system, and for that we will be using Phytech EFI. This is their Go EFI Classic Black. This is a direct replacement for any 4150 style or square bore carburetor. It contains 4 62 pound-per-hour injectors, and it will support up to 550 horsepower. To keep that classic carburetor look, the ECU is separate from the throttle body itself. Everything is controlled, monitored, and programmed through their handheld. Now, this is a great system that comes with everything that you need to hook it up in the car. Gaskets, its own wideband O2, all the wiring harness, and it also comes with a clamp-on style O2 bung. Now, if you don't have a way of welding an O2 bung into your exhaust, this is a great way to get an O2 into your system. If you've ever bolted on a carburetor before, the Phytech goes on just as easy. It even uses the same throttle bracket. An OEM quality O2 sensor feeds information to the ECU so the system can self-learn after initial startup. The ECU is very compact and it easily mounts in or outside of the engine bay. Up next, the small block struts its stuff in the dyno cell. We have our engine fired up and it was easy to do. The Phytech only needs to know a few things and we need to tell it what we want. Like we told it we wanted a 12.8 to 1 wide open air-fuel ratio, and that's about it. The tune-up is conservative, but that's for a reason.
It's all about cylinder pressure. Whether you're increasing cylinder pressure with boost or nitrous or dynamic compression ratio, your tune-up has to change accordingly to that. Because we're trying to run this engine on pump gas, the tune-up needs to become a lot more conservative. So that's why we only have 22 degrees of timing and a target air-fuel ratio of 12.8. This engine is actually really similar to a stroke Mopar that we did that had a 9.05 to 1 dynamic compression ratio, and it has similar airflow through the heads, so it'll actually be interesting to see how much this thing makes compared to that one in terms of power per cube.
All right, we're gonna find out like right this second.
All right, do it.
All right.
See what it does.
Everything looks good. Loads in okay?
Yeah.
Wow, that was uneventful like it should have been.
Yeah, but that's pretty good.
Ooh, nice. 426.9 pound-feet. Yeah, baby.
Yeah.
And 411.8 horsepower.
Wow. Yeah, peak torque right at 4,000. Peak power, yeah, right at 55.
Right at 55.
So
I think we're not going to stretch this thing out past 6,000. Well, let's raise the RPM and go to 6,000.
Yeah. See, just get a clear peak there.
Yeah.
And just back up that run. I mean, that was a nice solid run.
Yeah.
So.
How about that? 93 octane, 13 to 1.
And it made very similar torque per cube to that Mopar that I was just talking about. That's really similar. So that's very interesting.
Now, I'm not saying everyone should run out and put their engine at 13 to 1, but
no.
But we're doing this. This is an R&D engine. You know, we can do
Yeah.
whatever we want. We have controlled conditions to do
Yep.
it. So, all right, I'm gonna raise that up a little bit.
All right.
25 to 6,000. Let's see
what
if
she does.
let's see if she crests over. Got a little heat in the oil here.
Dang.
Oh, definitely. There
we
it is,
go.
right there.
Yep.
413 horse. Nice curve. I mean, at 6,000, you could leg it out more, but it's just going to drop.
Yep. Peak horsepower happened right at 5,400, so just a teeny bit lower, but that's pretty close.
That's excellent. 424.8 pound-feet. Boy, there's a.
It's a long line, isn't it?
That's a long line. The graph is nice and flat.
Yeah.
Oil pressure goes up. It has a little bit of vacuum in the manifold, not much, and it has vacuum
Yeah.
in the pan, so it's
Which is
not
great,
detonating.
Yeah. Wow.
All right, excellent. I'm
That's-
gonna shut this down.
Isn't that interesting though? That's cool, you know, that you can. I mean, that was the point of this exercise. This is very extreme. You know,
Right.
you're not going to go out and make all your street engines 13 to 1. But we did this for a reason, to show that it's not all about static compression ratio. It's about dynamic and more importantly, cylinder pressure.
Right. What did we learn? Well, we learned that the engine doesn't care how it gets cylinder pressure, right? You can do it a bunch of different ways, and there are many factors that have to come together. It's just not one over the other. Static compression ratio is important, right?
Yeah.
But it's just a number. Dynamic compression ratio is as important because it takes into account literally when things start to compress. Now there are other factors involved, like volumetric efficiency and how much restrictions in the intake tract, how much a cylinder heads flow,
Yep.
how high are you turning the engine. This is a very versatile engine because we could actually change a few things up on this, and then it is a race engine.
Yeah, exactly. But I mean, what it shows you is that your part selection is really important,
Mm-hmm.
and then what we've shown here is that your tune-up is also really important.
Yes.
If you plan on running pump gas, I mean, if we put race gas in it, we can crank the tune to it, and this thing will probably make a lot more power.
It 100% would be.
Yeah, but because we're on pump gas, that's another factor that needs to be thought of, is what the tune-up is going to be.
Right. The tune-up is very narrow because of the compression and because of the dynamic compression, because of what we're doing. The tuning window has narrowed. So again, because this is a controlled dyno condition, we can do this relatively safely.
Yeah.
And but
If you were going to put this in a car, and get it up to 180, 200 degrees, and then go and try and make a full hit on it,
on pump gas,
things would probably not work out so well.
they're not going to go your way.
Yeah.
But the foundation is really good.
Yep.
And I think it would be fun to see what else we could do with
I think
this.
there's a lot more tech that we could do on this
There
as
is
well.
tech.
With even what's on it right now, I think there's some more we could do. So
I'm a tech guy, so.
it's all mine. Data. All right. Heck yeah. If you want to see more cool tech like this, go check out our website.